So the thermodynamic temperature scale. In previous lecture, we did define the zeroth law of thermodynamics, and that law of thermodynamics was defined with a property called as temperature. Um, and yes, we have to define a temperature scale, and that temperature scale must be independent of the working medium, or we call it as a substance, and that we would call it as the absolute temperature scale. So, like in previous section, we derived the Carnot efficiency, and while deriving the Carnot efficiency, we did not mention any medium. Like our efficiency was not dependent on any medium or any substance. So we must be looking for a temperature scale that is independent on any medium as well. To see this, consider a situation that is shown in Figure A, and let we have different type of heat reservoir. We can have a high temperature reservoir, T1. We can have a low temperature reservoir, T3, and we can actually say like we have got a medium temperature reservoir, which is T2. There is a heat engine working between the high temperature and lowest temperature reservoir, which is heat engine C, and there is a heat engine which is working between the high temperature and medium, and that is heat engine A, and there is also a heat engine working between T2 and T3, and that is called as heat engine B. And obviously there is work done from heat engine C, A, and B. So efficiency, as we can say, like efficiency and is a function of temperature, and efficiency was derived by using the heat extraction from the high temperature reservoir and rejecting into low temperature reservoir. So we consider that the efficiency is a function of temperature. So that means like if I'm considering a heat engine, which is heat engine, let's suppose A, which is working between T1 and T2. So that means like Q1 and Q1 divided by Q2 would be a function of T1 and T2. The heat engine, which is working, heat engine B, which is working between T2 and T3, would be a function of T2 and T3, and that would be equal to Q2 by Q3. And then obviously Q1 by Q3, the heat engine working between the temperature between Q1 and Q3. Let's consider the last bit, which is actually the heat engine, which is working between temperature reservoir T1 and T3. So that means like Q1 divided by Q3. If I would write it like Q1 divided by Q2 multiplied by Q2 divided by 3. That means like what I've done, like I have multiplied Q2 and divide Q2 as well. So that means if I'm considering this side of an equation, that means like it would be a function of temperature by this analogy. That will be a function of temperature T1 and T3. And while if I'm looking at this side, that means like it will be a function of T1, T2, and multiply by the function of T2 and T3. But mathematically, this cannot be correct. That means like if your left hand side is a function of two variables, your right hand side cannot be a function of three variables. So that means like if your left hand side is a function of T2 and T3, your right hand side can be only a function of T1 and T3 and cannot be a function of T2. So we can conclude that if I'm writing Q1 by Q3, that can only be written as a function of T1 and T3. So having said that, we can say like generalizing this equation. So QH, if I'm writing QH by QL, that can only be written as TH by TL, and there is no other like equation which we can relate. So we have derived something which is mean like the heat are dependent on the temperature. the tiny temperature T, which can be anything. So T would be equal to TL somewhere and multiply by QH divided by QL. That means like if I'm looking for this particular temperature, I need to have consider three variables, which would be definitely a little bit difficult. So keeping these variable, I would say like these variable minimum, the minimum temperature that can be found would be the absolute zero, and which is actually minus 273.16, and the minimum heat that is can be found would be the heat at the triple point. So the heat at the triple point is the minimum heat, and the temperature at absolute zero is the minimum temperature. So now as these two would be known now, so we can consider temperature as a function of TQH now. So that means if I'm supplying heat to the system, the temperature rise would be actually equal to the heat supply to the system. Representation of the thermodynamic process in a TS coordinates. Up till now, in our thermodynamics lecture, we were considering mostly the PV diagram. And while we were considering PV diagram, we did said like the area under the PV diagram is equal to the work done. And that was the importance of the PV diagram. Now looking at the TS coordinates and obviously the importance of the TS coordinates. Um in a previous section, we considered the Carnot cycle. If you draw a Carnot cycle on a TS coordinates, it will be looking something like a rectangle. We will look at this kind of a TS diagram in the next few lecture. But considering it over here, we have got two different processes in the Carnot cycle. One was the isothermal process, and one is the adiabatic process. So we have got two isothermal process and two adiabatic process. So this is a Carnot cycle going from state A to B and B to C and C to D, and then obviously coming back to state A. Now, looking at the cycle itself and looking at the first law of thermodynamics and first law of thermodynamics for the cycle, let me write it like first law of thermodynamics, and which is du is equal to TdS minus dW. For a cyclic process, as we are considering it for the cyclic for the Carnot cycle, let me write it down the cyclic integral. For a cyclic process, the change in the internal energy, which is the state property, would be equal to zero, as there would be no change in the initial and the final state of the system. So we would be now having TdS equal to dW. So that means like the area enclosed in a TS diagram is equal to the work done in a system. So now as the work done, finding the work done is through the TdS, so we can find the work done using the equation TdS, which is alternative to the work done in a reversible cycle, which is PTV. In your own book, you would consider like you would find another concept, which is the area under the curve TS diagram, which is equal to heat supply. Make sure you just look at your book as well and try to understand that concept as well. I hope you understand the today lecture. If you have got any question in it, you can post in your classroom now. Thank you very much.